Hi everyone, and welcome back. Today we're talking about the traveling salesperson problem again, this time from the lens of approximation. And to motivate us, here is a traveling salesperson tour, approximating the letters TSP for traveling salesperson tour. Thanks, Prof. Ron. Just to remind ourselves of the traveling salesperson problem, we stated it as follows for a decision problem. Given some graph G that's complete, that is, every single possible pair of vertices has an edge between them, and distances along each of these edges, as well as some number k, does there exist a cycle through all nodes or vertices in our graph of combined distance less than or equal to k? So for instance, we could set k to 30, and then ask ourselves whether it's possible to find some cycle or tour of the graph, such that all of the edges when added together from this tour will have a combined distance of less than or equal to 30. On this graph, this particular tour follows this rule. But we might notice there are some weird things about this graph, namely that it doesn't satisfy the triangle inequality. Just to remind you all, the triangle inequality is just the property that we expect in most spaces, that the distance from some point x to some point y, plus the distance from y to some point z, should be greater than or equal to the distance if we took the direct route from x to z. That is, it shouldn't be possible to get a shortcut by going a long way around. We're going to add this particular restriction to our traveling salesperson problem to give ourselves a new problem, the traveling salesperson problem with the triangle inequality. This takes the same input as before, a graph G, except that in this case we're guaranteeing that this graph will satisfy the triangle inequality. We'll otherwise get the same restricted number k to determine what the maximum distance can be across our traveling salesperson tour. We can see in this new graph that for every single triangle we can get of 3 vertices, no 2 sides of that triangle will add up to less than the third side. Even with this restriction, the traveling salesperson problem with triangle inequality, or TSPTI for short, is still NP complete. It's NP for the same reasons the traveling salesperson problem isn't NP. We can check an answer, that is, a traveling salesperson tour that's given to us, in polynomial time by adding up the edges. The question that makes this slightly trickier is whether this is NP hard, as NP complete is a combination of a problem being both NP and NP hard. So let's briefly prove that this is an NP hard problem with the triangle inequality. And we'll do it unsurprisingly using a reduction from the traveling salesperson problem itself. We'll start, in this case, by looking at our original input graph and finding the maximum distance on the graph. So, using the graph that I have to the left, we can see that the maximum distance that we have is 10 to the 6th, right here. You can see that in this graph we haven't followed the triangle inequality. That is, the distance from A to C plus the distance from C to D is much, much less than the distance from A to D directly. So here's how we're going to make it follow the triangle inequality in our new graph. We're simply going to add that maximum distance to every single edge. Now wait just a second, you might be thinking to yourself, that seems like a really problematic thing to do. When we were talking about shortest paths, we specifically avoided that strategy when we were worried about correcting Dijkstra's algorithm to work with negative edges. However, in this case, because we're interested in what we could describe as longest paths, or paths that visit every single vertex, we know that every single one of these tours is going to have the same number of edges. So we can, in fact, take the strategy of adding a number to every single edge, and still have whatever the shortest tour was before retain the same relationship in terms of distance to other tours afterwards. We're now going to set our new value of k to be the number of vertices times that cost of the maximum edge, plus the original value of k. So before in our graph, where we might have been interested in finding a tour of distance 5, we're now interested in finding a tour of distance 4 times 10 to the 6th plus 5. In total, this reduction takes polynomial time. Finding the maximum edge distance is proportional to both the number of edges and the number of digits in our biggest integer in the problem, both of which are part of our problem input. Adding this to every edge again takes time order the number of edges. And finally, adding this particular number to create k is just a simple individual computation. Now we observe 2 properties doing this. First, as we described before, every TSP tour that we had before has had its cost increase by the same amount. That means if a tour cost some amount x before, it must cost 4 times 10 to the 6th plus x afterwards. Following this transformation, it makes sense that if we had a tour of cost 5 before, we have a tour of cost 4 times 10 to the 6 plus 5 afterwards. This gives us our if direction on its own. We can actually also see that it gives us our only if direction. If we have a tour of some cost 4 times 10 to the 6 plus 5, or in general, the maximum distance times n plus k, then we know that that must imply that the original version of that tour in our traveling salesperson problem had a cost of that minus that amount. The thing we might be more interested in checking, though, is have we now made it so that we satisfy the triangle inequality? We'll note that if we assume that all of our edge weights were originally non-negative, which we can in TSP, then we know that all of our edge weights will now be between d max and 2d max, which means it would be impossible for any triangle to not satisfy the triangle inequality. The sum of any two edges must be at least 2d max, and no individual edge can exceed 2d max, so the triangle inequality will always be satisfied. Now, how do we approximate this particular problem? It might not be clear yet why we'd be excited to have the triangle inequality present. The main reason we're excited is because it allows us to create a 2 approximation of the traveling salesperson problem. Let's look at how we do it. First off, we observe that we're bad at finding traveling salesperson tours. It's a tricky thing to do. But one thing that we're good at in a graph with distances in it is finding minimum spanning trees. So the first thing that we're going to do is find a minimum spanning tree of our graph. One thing that we can observe from the minimum spanning tree is that we know that it must cost less than whatever the optimal solution of a traveling salesperson tour is for a graph. That's because if we take any edge out of our optimal solution, then it must create a spanning tree, as it'll have n-1 edges that are connected together and touch every single vertex, which means that our minimum spanning tree must cost at most that amount, if not less. Here's now how we're going to construct our tour. First, we're going to make an awkward tour, one that's illegal by our usual rules for a traveling salesperson problem. And we're going to do that by simply tracing loops around our minimum spanning tree. We can think of this as outlining the minimum spanning tree. And what this will do is, by potentially adding the possibility of revisiting vertices, give us something that starts to look like a tour. In this case, we can see that we go from A to C, back to A again, then back out to D and back to A, then to B, E, back to B, and back to A again. If we take this particular, quote, tour, unquote, we can see that it's not the normal kind of tour we would expect for this graph, but it does visit every single vertex. We observe that the way that we constructed this, quote, tour, unquote, is by using every single edge in our minimum spanning tree twice. So, we know that 2 times the cost of our minimum spanning tree must equal the cost of our awkward tour. Next, what we're going to do is correct our tour. That is, we're going to go around the tour that we've created, and every single time we see that we're going to visit a vertex that we've already visited, we're going to replace the edge that would have done that with an edge that will go to the next vertex in the tour instead. So, if awk, our not quite tour, contains an edge u, v followed by an edge v, w, but we know that somewhere prior to u we had already visited v, we're going to replace that edge with u, w. It's possible that we've already visited w at that point too, but we're going to let the next step of processing repeat this same rule for correcting awk. And by doing this, we're going to be able to simplify our original awkward tour into a correct tour. Let's look at how this process works out in this graph. Here we can see that our first step is to go from A to C, if we imagine we start from A and start moving counterclockwise. And this gives us a distance 5. And at this point, going from A to C, we haven't visited any other vertices, so this is okay. Our next step would then be to go from C back to A again. However, we've already been to A. So rather than going to A, we're going to skip from C directly to D, our next step. We'll note that here we're going to replace the edges from C to A and from A to D with one edge from C to D, and this is where the triangle inequality comes in. We know that the distance 10 from C to D must be less than or equal to the distances that were originally present because of the triangle inequality. That's 5 plus 6 in this case. So we haven't increased the cost of our tour at all by making this replacement. We continue to repeat this process. The next leg would go from D to A, but we've already been to A, as we said before, and we're not at the end of our tour yet. So we're going to replace this with an edge from D to B, where we haven't been yet. And this again gives us a relaxation of 9, which is less than or equal to 5 plus 6. We can continue this process to go from B to E, and then from E back to A, making our final relaxation, and thus concluding the construction of an actual legal tour. We can see that every single time we replaced one of these pairs of edges that contained a repeat vertex with an edge to try to avoid that repeat vertex, we never increased the cost of our original awkward solution. We only could decrease it or keep it at the same cost in the case of this edge 7. So, we know from this that the cost of the solution for our algorithm, as this is the approximate tour we'll now use, has to be less than or equal to the cost of our quote awkward tour from before. If we take all of the properties we've just shown together, we show that we have an approximation that works. That is, alg costs less than or equal to awk, which we know has the value of 2 times the cost of our minimum spanning tree, which we know must cost less than or equal to 2 times the optimal solution. So, altogether, alg is less than or equal to 2 times opt. This is a pretty cool approximation. A worthwhile question might be, is this something that people actually use? And the answer is yes, as a starting point. After applying this sort of approximation, one might have a reasonably good traveling salesperson tour, but there's some things that heuristically, not necessarily guaranteed, but heuristically make things much better. A big example of this is the pairwise exchange heuristic. This is a rule that says if 2 edges cross, it might be worthwhile to check if uncrossing those edges would reduce the cost of the tour. In the general traveling salesperson problem, this isn't necessarily guaranteed to help anything. The fact that edges cross isn't meaningful. But in a map or another Euclidean setting, this is usually a fairly good sign something inefficient has happened. So it's worthwhile to check whether replacing 2 crossed edges with 2 uncrossed edges, which otherwise still gives you a tour, will help reduce the total cost of your tour. Now this is a heuristic. It's not an approximation with some official bound. However, it works quite well in practice. Notably, the pairwise exchange heuristic is giving us an opportunity to check, in polynomial time, a bunch of different things that might help us optimize our tour. But it's not ever going to make a decision to uncross 2 edges unless it's actually going to improve the tour. So things are never going to get worse than our 2 approximation, but oftentimes they get much, much better. If you're ever interested in checking this out further, Concord is a tool that's offered by Arizona State University that allows you to check traveling salesperson problems, like the ones we've been talking about, in order to see what the optimal solution is. And if you apply just this approximation, which in other semesters would potentially be a homework problem, you'll find that you often get within 2% of the optimal solution. That's a pretty concrete example of why it's still worthwhile to come up with approximate solutions for problems that we describe as too hard to solve in a tractable way optimally. Having a traveling salesperson tour that costs 102% of what the optimal solution would isn't that bad. There's a little bit of additional savings that you could get, but it sure beats not having a solution at all. How well can we approximate this? For a long time, for the traveling salesperson problem with triangle inequality, 1.5 approximation was about the best we thought we could do. It's interesting. When something like this happens, where you have a nice round number like 1.5, and for years people can't prove anything better, people start to believe there might be some mathematical property that makes this a fixed bound, but nobody could prove that there was a fixed bound for this either. There was some natural thing about 3 halves that would ensure that the traveling salesperson problem would follow this. However, with the triangle inequality in place, a new approximation algorithm was found in 2011. And this one was a 1.499999 and so on approximation algorithm. Basically 1.5, but just a tiny bit smaller, enough to show that 1.5 didn't have some natural law of the universe encoded within it. This might seem like a very small thing, but it's a big deal in mathematics because it's likely to lead to a bunch more people for the next 10, 20 or more years researching ways that we can approximate better. Why aren't people looking for approximations for the general traveling salesperson problem, though? Why does it have to have the triangle inequality or some other restriction? As it turns out, the generalized traveling salesperson problem is inapproximable. That is, unless p equals np. Why is that? That's because if we had any polynomial time algorithm that could provide a constant factor of approximation, 1.5, 3, 10 times optimal to generalize TSP, we could use that using a reduction similar to what we had before from undirected Hamiltonian cycle to solve undirected Hamiltonian cycle in polynomial time. And I'll let you think a little bit about how that might work. You might be interested in who even works on these types of problems. Who's interested in finding newer, better approximations for these traveling salesperson problems or other optimization problems that come up in the world? In fact, one known researcher in this space who works on approximation algorithms for graph problems is an alum and a friend of mine. Salil Shram is another Harvey Mudd alum who works in the space of algorithms. She works in approximation algorithms for all kinds of different things, and she's going to be starting as a Stanford professor in 2021. I highly recommend checking out her videos online if you think that this could be a cool future research area for you.